Okay, so KD tree, it implements point set, and it needs a constructor. Takes a list of points. As before, I'll import using Alt-Enter. And then I need my nearest method. So this one I'm going to set override. So now I'm about ready to get going. I'm just going to return null for now. Oh, and I have a typo. Should be lowercase d. And that's that. Okay. So what should I do next? Well, I kind of want to write some tests. I'm going to jump in straight into testing because I can. I don't know. You could do either way. But I'm going to go to testing because I know this is going to be complicated, and I'll feel better if I have tests waiting for me already. I think. Let me think about this. Well, it's kind of complicated because I'm going to have to write this whole constructor and this whole nearest method before I can get any feedback. So writing a test now. Actually, I'm not ready to write a test, I decided. So instead, what I'm going to do is I'm going to do the same thing I did before, well, where I'm going to have a main method. And I'm just going to take this naive point set, and I am going to copy myself this code. But I'm not going to call nearest. All I want to do, because I know the constructor is going to be harder, I'm just going to do this stuff. I'm going to say, I want to make a KD tree. Okay. And this way, I can at least see what's going on. All right. So, is this what I want? This is a small little tree. I kind of want something harder. You know what I'm going to do? I'm going to take the example from the slides. And that way, I'll feel like I'm doing something really useful. So in particular, I'm going to go into slides for multidimensional data. I'm going to go find the example that I've already watched as a student in 61B. Let's see, KD tree insertion. There we go, KD tree insertion. Okay, so what points did I get? I had 2, 3. Okay, sorry, got interrupted. So where was I? Oh yeah, I was going to insert. So my goal is I'm going to try and write a constructor for KD tree, okay? And it's going to insert the points from the example. And the reason I'm doing this is that way I can easily check my work using the visualizer. Or I don't know, maybe it'll look terrible, but we'll see. Okay, now we do Z for 2. Okay. Now one difference, of course, is that the example in the slides, as this is a map, here we have a point set, so there's no reason to do 4, 2 twice, so I guess I'll skip that. Well, you know what? Actually, I'm going to do it. I'm going to do it because I should only end up with 1 copy. All right, so now we get up to 4, 5. Okay, 3, 3. 1, 5. And there's one more, which is 4, 4. All right. So that's a little annoying, but you know, I'm not shy about doing those kind of programming tasks. Take a few minutes, but it'll pay off in the end. All right. So that's going to be my goal. After I create this, I want to be able to visualize and see this thing. All right. Let's shrink this all down. All right. So now at this point, I'm going to start hiding my code again. I don't want you to copy this either. All right, so my constructor. Well, it's clear that a KD tree needs to be a tree of nodes, so I'm going to need a root and a node class. So my node class, I'll put at the top of my file, I guess. So I'll say private class node, and I need to store a point, clearly. So public, or no, private point p. What else needs to go in node? I guess horizontal versus vertical? I don't know. Seems like one way to do it. I guess you don't technically need to store it because every other level is horizontal versus vertical. But I'm going to put it in the node anyway. I guess it'll be a little less memory efficient, but it'll be easier to program, I think, if I do it. So I'm going to say private Boolean orientation. And then I'm going to do a little trick where I'm going to say something like private static final Boolean horizontal equals false. It's another way to do this using something known as an enum, but I won't describe it here. But this way, I can just say equals horizontal or equals false, or sorry, equals vertical, and my code will be more readable. Okay. Alrighty. So I think maybe that's all a node needs. I mean, I could try and store these lines, or even the regions owned by the spaces, but it's not clear to me that I'll need that. Okay. So what I will do next is just try and use just these. Okay, I'm going to try and keep things simple at first. And if I need more stuff, I'll do it then. The key point is I want to think about as little as possible at any given moment. So now I need to go through this list and build myself a KD tree. Okay, so now I need to really reflect on what this demo does. Okay, so I guess I'll go, well, one resource I would definitely go look at is my solution to the binary search tree insert, because this is going to be something kind of similar. So I will admit I actually know it pretty well, but just for the sake of kind of demoing how one might think about things, I'm going to say, let's make directory, I think, which lab was the BST lab? Was that 8? Yeah, okay. 8. I'm going to lab 8. And I'm going to get my solution, which is here. Lab 8. Solution. Canonical. Oh wait, geez, wrong lab. Should be 7. Oh well, I'll fix it. Solution BST map. Okay, so I finished that lab at some point, and I'm just going to open this thing in Sublime and use this for inspiration. All right, so here's some BST map, and when I look at the put method or add method, okay, we have this notion of a helper method. Okay, and here it takes a key, a value, and a node. It's null, return. All right, so I'm just going to kind of work from this as my pattern because I know that it's going to be something fairly similar. So to insert these points, I think what I want to do is I want to make an insert method, but it's private because no one's supposed to be able to add to the KD tree. So I'm going to have an add method. I give it a point P, and it's your type void, and this adds a point to my KD tree. Okay, so what happens? Oh, I need an instance variable for my root. So I'll also, in my KD tree, I'm going to create an instance variable. So private node root, and in the constructor, I'll say root equals new node. Do I want? No, we don't have to create a root yet. I'll not do anything. All right. Oh, actually, you know what? I can write my constructor. That should be fine. So I'm going to say, for point P in points, add P, or root equals add. That's kind of interesting. So I start from nothing. How do I do that in another program? Put helper. Yeah, all right, that's right. I could just say root equals add. That's kind of interesting. Yeah, root equals add P. Oh, I see. So my add method actually, I'm not going to have an add method with only one argument. I'm only going to have an add method that takes both a point and a node. Okay, because I'm copying this put helper idea. So point P and node N. So then in my constructor for KD tree, I'll say root equals add the point, and then I'll pass the root as the second argument. Okay, so there's a problem here. Oh, the add method's supposed to return a thing of type node. Okay. All right, so I'm going to write my add method. Okay. So this add method. All right, so if the node we're looking at is null, we're going to return a new node that contains a point. So I need a node constructor. So public node point P given P. P equals given P. Okay, so I've created a node constructor. Now I create a new node. And so now that I've done so, I need to, so I've got this part done. I'm not tracking size, so I don't care. So now I need to do some comparison. Okay. So we will do int compare, the result of some comparison. We need to do a comparison of some kind. All right, how do I know what to compare? Well, it depends on what level I'm at. I see, okay. So the node could be null. All right, I think what I'm gonna do is add a Boolean to my add method that tells me whether or not this is a horizontal level or a vertical level. So Boolean orientation will be an argument to my add method. And the idea there is I just want the add method to know what it's supposed to do. Okay. And then when I first call it at the very root, that is a horizontal, or sorry, depends on what you mean. Which one's which? Horizontal, or splitting horizontally. So I'd say the root is horizontal because it cares about the x direction. Oops. Okay, so add P, root, horizontal. Okay. I mean my nodes needs to know its orientation as well. Okay. Yeah, all right. So when you give a node an the node constructor needs both a point and an orientation. Node P, pass it an orientation equals P. Oh. Return new node P orientation. And now, if it is not null, then we're going to do some comparisons. So int compare equals I need to compare n's point with P. So I need some kind of comparison that I call on end.P and P. Where does that compare come from? Well, it comes from the orientation, I guess. So, All right, so I guess I'll just have a compare function. Compares two points based on their orientation. So I have some all right, so I have a compare function. It's going to take three arguments. It's going to take a point, another point, and the orientation. And so that method will be private as well. Private int compare nodes. Let's call it compare node, or compare points. Okay, so private int compare points. It takes point A, point B, and a Boolean orientation. If orientation is horizontal, then you need to compare the 2 points using their x coordinate. So I'll return A dot. Oh, actually, I remember there was the thing in the spec about using double to compare points. The thing I'm a little worried about is if points are just barely off, rounding error is kind of a pain. So let's see, double dot compare. Yeah, I'm gonna use double dot compare. That's just easier. That's just safer. So I'm gonna compare a dot x with b dot x. Oh, sorry, a dot get x with b dot get x. Otherwise, I'm gonna return double dot compare a dot get y, b dot get y. Okay, so at this point, I have a comparison. That seems pretty straightforward. Looking back at my BST, if the comparison is less than 0, then I will say that my nodes then n.left. My nodes don't have left and right children. Okay, well that seems like another big thing I need. So my node class also needs a left child and a right child. Okay. Now for consistency with my pseudocode, which maybe I should have been looking at the whole time. Yeah, I just called it left child and right child. I guess I'll make a note that the left child also refers to the down child. And right child also refers to the up child. Okay. So that's just reflecting the fact that the left is equivalent to down. So I'm just going to call it left child, even though sometimes it's down. So if the comparison is less than 0, we will say that the left child, so we haven't hit a null yet, so we need to say that the left child is going to be the result of adding p in, and then the opposite of orientation. So the not operator in Java is exclamation point, so there we have it. Okay, else if the comparison is greater than 0, then the right child is going to be the result of a, p, n, not orientation. And if it's equal, well, then we don't do anything. And finally, we'll return the node. So I've written an add method that will allow me to add points. Okay, at this point, I think I'm ready to go and try running the example. So let's see, I'm gonna move the code over, and I'm gonna try running it and see if it crashes. And if it doesn't crash, I'm gonna use a visualizer. Uh-oh, we got some problems. Oh, what's this doing here? I didn't mean for this to actually get imported into my project. All right, go away BST map. Now it's gonna delete it. All right, bye. And so now that's gone. Okay, whatever. We don't need to look at that anymore, I don't think. All right, let's try again. Okay, did it crash? Infinite recursion. Okay, so something's wrong. So why did that happen? I'm gonna look back at this thing. Oh, we need to call it on its left child and right child. Okay. Yeah, I forgot to do an important thing. So when I'm traversing the tree, I need to actually pass along my child. All right, so now we run it, and we get, all right, completed with exit code 0. So now, let's use the visualizer